Thank you all for being here, and thanks, Andre, for having me over. My name is Srinivas Shakkottai, and I teach at Texas A&M University. The kind of stuff I've been doing, so I got my PhD at Illinois Urbana-Champaign in 2007. And then I was a postdoc at Stanford for about a year, and I've been teaching at Texas A&M since early 2008. So I've been there about a year, about 2 years now. So the stuff I'm going to talk about today has to do with latency and cost trade-offs, in particular for peer-to-peer assisted content distribution. But there's a much more general problem here on queries and how you kind of distribute them based on the latency that they suffer. So before I get into the talk, I just want to kind of give a little overview of the kind of stuff I've been doing and where it fits in with networking in general. So this is a picture of the internet created by Brad Huffaker at CADA. So CADA is a place where I interned a couple of times. I've been wandering a fair bit, and I spent 2 or 3 months in a whole bunch of places. Now, the picture here basically shows the internet at what is called the AS level, the autonomous system level. So basically what it indicates here is that the location, the radial location of the particular autonomous system is based on the kind of number of customers it has, the amount of traffic it carries kind of stuff. And the location on the ring is based on geography. So this is North America, that is the Atlantic Ocean, Europe, Asia, Pacific Ocean. So the reason why I put up this picture quite often is that when you look at this, you see that there's a tremendous amount of interconnectivity between multiple different locations. And very often, we don't really exploit this diversity. What I need might not be just in one location, but it might be in multiple locations. So really, the kind of stuff I've been doing kind of in the space of network control and network algorithms. I'm going to talk about content distribution today. But in general, I've been working, for example, on protocols which take advantage of the multiple routes between a source and a destination. I've been also looking at how to provision QoS on an end-to-end basis. I've been looking at access methods. For example, if I'm sitting around with my laptop, I see multiple different access points. Can I somehow split my traffic and take advantage of the fact that I might have diversity in terms of number of channels available to me? Multicast takes advantage of the idea that there might be multiple people interested in the same thing. So why should I transfer multiple unicasts to somebody when lots of people want it together? In particular, the application we were looking at there was kind of like in a football stadium where people have smartphones and people want to look at pretty much the same thing, scores perhaps, replays, and that kind of thing. So this all has to do in the space of network optimization and control. Also been working on network economics. How do I price this thing? Each of these kind of boxes is what is an autonomous system. Google, for example, is an autonomous system. The guy in the middle over there is Verizon Business, which is AS number 701. It's had a long history. It used to be UUNet, then BBN Planet, and finally Verizon bought it. Now, there's a good deal of competition between ISPs which operate at different levels. So good pricing models which are stable is a very interesting question. This plays right into net neutrality, because the economics has to do with the QoS as well, because you cannot have QoS unless somebody is going to pay for it, and you can't have anybody to pay for it unless you give them QoS. So economics and technology really ties up in the space of the internet economics, because you need good pricing schemes, you need to know what ISP competition is likely to lead to, and that kind of thing. Finally, and this is where Andre comes in, I've been working a fair bit with CADA on network topology, why this thing looks this way, how does it evolve with time, understanding the performance of protocols in the real world, and that kind of thing. So I can, if people are interested in this space, I can of course spend some time. I'm here till the end of next week. So the thing I started with just a little while ago was, if I want something, why should I go to the other end of the world to fetch it? This here is Houston, which is close to College Station, which I'm at, and that is Bombay in India. Now, if I want a piece of content, there is no reason to ship it from Bombay. You can get it from multiple different locations. Indeed, if you have queries to be processed, you don't need to process it at one particular server farm or one particular cluster. You might have multiple different locations. You might be able to process it. So the question really is, how do we take advantage of the diversity present in where my query or my content can be serviced from? So this is a little picture which is generated by Pando Networks, which is a startup with whom we have had some contact. So they basically illustrate the fact that when the internet was created, like this was a little earlier, but roughly speaking, the internet really took off in the early 90s. The big applications there were FTP and email, right? So the idea was, because the internet was created to ship large data sets between big labs like cyclotron data, which is these huge massive data sets. You ship them from SLAC in Stanford perhaps to Illinois where they have a supercomputer center. So you notice FTP was enormous and email was in existence. And then people realized that, hey, we can use this internet for many other things. In particular, the web started growing up. And so web traffic really took off in the mid to late 90s. But more recently, the understanding that queries can be processed from multiple locations. So if I have a file on my machine, I can give it to somebody else. If somebody else has it, they can give it to more people. So in other words, using end hosts as servers has really taken off in the past couple of years. And you notice that in 2006, for example, a good deal, about 70% of the bytes as these guys measured, various different measurement traces seem to indicate anywhere between about 60 to 70 odd percent or 75% of the bytes on the internet seem to appear from peer-to-peer traffic. Now further, this curve stops at 2006. More recently, there was a report in Nanog this year on the fact that there is a good deal of video traffic growing up on the internet. And so the P2P in North America for file sharing seems to be going down. But peer-to-peer for video distribution is really popular in East Asia. In China, there are these things called PP Live, TV Ants, QQ Live, and so on, all of which are using now peer-to-peer ideas for video distribution. So the question, high level again, is how do we use kind of a distributed resource like peer-to-peer servers or multiple clusters in a server farm to service my requests rather than servicing it in just one location. So I'm going to talk about, these two I'll talk about in fair detail, and the third one will be a little less. So the first question I'm going to deal with has to do with latency and costs in so-called ISP-friendly peer-to-peer. So the idea here is that I can service my query at multiple locations. There is latency at multiple locations, and there's a cost to get there. This might be a transit fee, it might be round trip time, it might be a bandwidth cost. So the question is, how am I going to do load balancing in such a system in a very simple, fast, and distributed manner? So I need to do this in a parallel fashion. Now the second question I'm going to talk about has to do with file sharing. So very often when things get popular, they get popular very quickly. This is called a flash crowd. I'll give a little more idea of what it means in a little while. But really, we're going to understand what constitutes a flash crowd and how do I service such a crowd. Do I use a server alone or a fixed capacity content distribution network? Do I use peer-to-peer, or do I kind of join them somehow together? And finally, if I do get time, I'll put up a slide or two on using peer-to-peer for video delivery as well. So the first problem has to do with latency versus costs in so-called ISP-friendly peer-to-peer. The motivation is the following. Supposing I have multiple different internet service providers. Say Comcast is one of them, Suddenlink is another, Roadrunner is one more. Today, peer-to-peer, when I ask for a list of peers to communicate with, what it gives me is a list of peers from all over the place. So in particular, if I belong to Comcast, I might get some peers from there, some peers from there, some from here. Now is that good or is it bad? Now it is good in the sense that it gives me the best peers. I get the peers who are most likely to be able to give me something worthwhile. It is bad in the sense that internet service providers have a cost of transit traffic between each other. So if I have to move traffic from here to here, it costs something. If I have to move from there to there, it costs something, and so on. So internet service providers have been kind of trying to tamp down on peer-to-peer traffic simply because it increases between ISP costs. But if you just look at costs alone, you don't realize that the latency of users can suffer if you just force them to live in one particular ISP. So to give a clearer description of what the problem is, we would like a system which takes into account both transit fees and latency. Now this is very important to this, the distributed query processing as well, which I will just mention in just a second. So I can reduce transit fees by simply localizing traffic. I just keep it local, no transit fee. I can reduce latency by choosing the best guy who can serve me. The question is, how do I handle both of these together? How do we achieve this optimal operating point? So this tussle between fees and latency is what I want to talk about. And there's a bit of work in this space. Very often it's kind of heuristic. It doesn't quite capture the essence of the problem, in my opinion. But nevertheless, there are some solutions which work fairly well. And what I'm going to talk about is a little bit about the analytical solution to the problem and how we implemented a very nice distributed solution for this. So here is my problem. So supposing, for example, say I'm thinking of a query processing location. So basically, these guys are all front-end clusters, or basically when my query shows up, it is handed off to some particular front-end. These requests which are coming down here are all the queries. Use a pen. So for example, this is a particular location. There's a fair number of requests which are coming to this front-end. Now this front-end, usually what you would think is it is connected or is associated with some back-end processing engine. It could be a cluster of some kind. So all these nodes could be some kind of processors. And this front-end's job, perhaps, is to assign these queries to that back-end cluster. Fair enough. This happens if there is just one front-end and one back-end available to me. What happens if I have multiple locations? So here what the objective is I have lots of requests coming in here and a fairly limited processing capability here. Here I have fewer requests but a larger amount of processing capability because I have more nodes there. So really, I would think that, hey, I should send some of these requests over there so that they can be handled quicker. However, the quickness or the latency of handling is not quite everything, because there could potentially be either a round-trip time latency between these locations or a bandwidth cost, or in my ISP case, there could be a transit fee between them. So really, it's not purely about latency. It is both about latency and fees. Now, as I was just saying, exactly the same ideas apply to load balancing of queries. I have queries which show up. They have to be handed off somewhere for processing. Do I hand them off to my local cluster here? Do I hand them off somewhere else? What do I do with them? So that is really the requirement. This business of steady state and transient refers to the fact that there could be clusters for whom the request rate is less than the available capacity, while there could be other clusters for whom the request rate is bigger than the available capacity. So clearly, I should hand off some part of this over here. But what fraction? How do I do it in a dynamic fashion? How do I measure the latencies in a feedback fashion? How do I do it in a simple fashion so that it converges quickly and efficiently? So that is my first problem here. So we have a little bit of notation here. So all I'm saying is that this superscript refers to the backend cluster, while a subscript will refer to the front end, which does the assignment. So really what I'm saying is any cluster, we assume the cluster name I is assumed to have C sup I queries per unit time capacity. So for example, this cluster out here would have C sup 1, C1 amount of capacity for processing queries. The requests arrive at the front-end server, which I'm calling a multi-track M-tracker or whatever a front-end server is, as some process. It could be a Poisson process. It could be anything really, with certain parameter as x sub j queries per unit time. So to go back to my picture, I might have requests coming in here at x sub 1 requests per unit time. So the question is, what do I do with this x sub 1 request per unit time? Do I send them local? Do I split them up? What do I do with them? So the important thing is I actually don't need to know either of these for my algorithm to work properly. I can work with measured feedback latency signals, as I'll illustrate when I get to the algorithms. So anyway, so we have a kind of timescale separation argument here. We say at the large timescale, the load changes. So in my P2P system where I've taken several measurements, it's the things which get popular together. So of the order of like 20 to half an hour, 20 minutes to half an hour, nothing much changes in terms of the number of requests per second. So I can think of each of these as kind of half an hour time slots. Now the capacity of the systems, each peer-to-peer cluster, or if you're thinking of back-end clusters, the clusters themselves could be dynamic in that some things could go online, some things could go offline, and so on. So I assume that in the order of minutes, the cluster capacity or the peer-to-peer cloud capacity itself can change. So this was like half an hour intervals. This could be something like 10-minute intervals. Finally, I have to do my traffic assignment. Where am I going to route my traffic to? This I do of the order of seconds. So really, I'm first going to just deal with this, looking at capacity as constant, load as constant. And then I'm going to go up here and say, how do I change the capacity? Finally, I'm going to talk about how does the load change. So the notation which we had, it's exactly the same thing that I had earlier. So we had this x sub j, the request rate at the front-end server j, in number of queries per unit time. And an assignment matrix x is the way I assign this. So what does this mean? So I have this front-end server j, and it has multiple options. Say he has 3 options. So then he has to decide how much of the traffic he is going to send to option 1, which will go to the cluster 1, how much to send to 2, how much to send to 3, and so on. So basically, this is the way the front-end server j partitions his load. Now there are multiple front-end servers, so each one is doing this partitioning. We call the whole matrix of all the partitions, the assignment matrix, as capital X. So is there any question on what this means? Basically, to give another illustration of what's going on, I have an x sub j coming in here. I have an x11 going in here, an x12 going there, and x13 going here potentially. Similarly, this guy can send traffic to each one. So this, the assignment matrix, would be a 9 by 9 matrix, because each guy has potentially 3 options. And so you can have, some of them could be 0, of course, but potentially this is a 9 by 9 assignment matrix here. Oh, sorry, 3 by 3, a total of 9. Yes, sorry. So there we have our assignment matrix. The question is, what am I going to do with this? So again, to just recollect the notation, the origin is always a subscript. This is the front end where the query is actually received, and the superscript is the destination to which the query is routed. So that's the notation all over the place. So x sub j sub 2 means that the jth origin will route this much amount of load to that particular cluster. And obviously, I cannot drop any queries. So the sum of the partition or the sum of the assignments must add up to the load at that particular front end. So the question is, how am I going to do this assignment? Now, in order to understand how to do the assignment, I need to have some idea of what latency is likely to look like. So what is latency? So really, I send you a query, and after a little while, you respond. That little while or a long time depends on how many others are also querying the same thing. So this is a very simple latency function. It comes from queuing theory, and it's really straightforward to understand what's going on here. So basically, the idea is I have an engine which can respond to queries at rate c sup I queries per unit time, and I feed in a load at a rate z sup I number of queries per unit time. These things go and sit up and queue up, and this query engine keeps processing them and throws them out. The question is, somebody comes in here, he sits there, he kind of goes across, gets served, and gets out. So the question is, how long is he going to sit there? What kind of shape of the function is this going to look like? And the answer is, it always looks convex increasing, because the idea is, in fact, that if you look at that expression, as z is much smaller than c, you have very low load. As z comes close to c, the denominator goes to 0, and therefore the whole thing goes towards infinity. So the idea is, as I increase the load on a particular server, the latency, the time between the arrival and departure, is going to increase in a convex increasing fashion. And this is true not only of such functions, it's true of pretty much any system you choose to measure. Like this is true for deterministic job size. It is true, for example, in peer-to-peer systems, which I've got some measurements on. It's pretty much always happens that as you get closer and closer to capacity, the number of the latency involved. In fact, if you look at the 101 at 6 o'clock, you'll see this in action. So as you get closer and closer to capacity, you have huge latencies. So the total latency, which is my unhappiness of my users, so the per user latency was that, and the number of users per unit time or number of queries per unit time is z sup I. So the total latency suffered by all the users getting in here is this. So how does that play into the picture of this distributed cache, distributed query processing? So that was my picture, right? I had traffic coming in or requests coming in from multiple locations to a particular front end, and that in turn went to the back end to be processed. So how much traffic is coming in? So we have basically traffic from there, there, and there to be summed up. So basically, we have traffic from front end R coming to cluster I. So at the cluster I, the total load is just the sum of traffic which comes from the various different locations. So in that particular diagram, the cluster number 1 is handling x from 2 to 1, from 3 to 1, and 1 from 1 to 1 itself. So that's why I have to sum all the traffic which comes in. And of course, the total latency has some expression. I'm just using the MM1 expression here for illustration. So I just stick in z is equal to the total load coming in, and this is my total latency experienced at some particular cluster. So that is my latency. Great. What else do I have? I have this transit fee. As I said, a transit fee can be round trip time on the link, which is potentially a propagation delay plus queuing delay. It could be the bandwidth cost, because I have to pay somebody for bandwidth cost. In my case, what I'm saying is it's a transit fee between ISPs. So whatever it is, there is a certain fee which is charged, or which is a cost incurred for transferring users from one location to another. And that is charged on a per query basis. So if I transfer one user from R to cluster I, R is the front end where the user actually showed up, and I is the cluster where it finally gets processed. Per user, it costs me that much. So again, we have to find out how much is the total transit fee to get to a particular cluster, and that we do by simply summing up the total load. So in other words, I have traffic coming in from 2 to 1, from 3 to 1, and from 1 directly to 1. 1 to 1 costs me nothing, 2 to 1 costs me per user something, 3 to 1 costs me per user something, and that is really what is being summed up here. So this is the total transit fee, or the total cost in getting to the cluster, right? So much for that. So what is my system cost? My system cost that I look at is the total latency plus the total transit fee. So we developed an expression for the latency, which was basically load divided by C minus load. So if you get rid of this, this basically says for any particular cluster I, what we have is the latency on that cluster plus the transit fee to get to that cluster. And then I have to add up over all my clusters, because that is my whole system. So if I have multiple locations, each location experiences a latency, a total latency. Each location, there is a cost to get there. That is the total cost of a particular cluster over all clusters is the sum. All right, so we need to design a controller that somehow minimizes this. This really is the unhappiness of the world as far as I'm concerned. So how do I minimize this unhappiness? Right? It costs me, and latency costs my users because they get unhappy. Transit fees cost me because I have to pay it out finally. So the question is, how do I design such a controller that is both simple, distributed, and fast? So these are the three things. Distributed in particular is very common among network optimization folks, simply because there are millions and millions of flows on the internet. There is no way on earth you can do an optimization with all those flows sitting in one particular central computer. So distributed processing of such optimization problems has been a big question, and there's lots of ways of handling this. Now, so the objective really is, this is my unhappiness. There is a lowest unhappiness that somehow I want to attain, and I want a distributed way of getting there. So this makes me as little unhappy as feasible. Now there's a whole bunch of controllers which can do this. Oops. So the question is, how do I solve it? And there are lots and lots of optimization techniques, and I'm going to pick one which is particularly useful for this problem. So usually there are some which are fairly complex in terms of the computation. You can do centralized computation in one big machine. And these methods, although they give you very accurate solutions, require a lot of processing in a particular machine. So the other methods, which I've put down here, these are some of them, are basically distributed methods. So there's Newton methods, there's log linear learning, best response, which means do the best thing given the state, gradient descent, and so on. So what I'm going to describe is actually a coupling of these two, which is particularly suited for this thing. But really what I wanted to say here is there is a whole bunch of tools which have been developed in the kind of OR optimization, the operations research literature, which are useful for such problems. And so very often when we solve network optimization problems, you can go and look in this bag full of controllers and pull out one which is most suited, and then show that it's suitable for your particular application. So I'll tell you what my controller is going to be in a second. But before doing that, I need to know what the kind of per unit cost is going to be. So what does this mean? I told you that the total cost of the system is this, the total latency plus total transit fee. Now the question is, if I take a decision on how much load to send to a particular cluster, how does this cost change? So for example, I have two clusters, and I have an arrival rate of requests coming in. Now if I move some to one cluster and some to the other, maybe it's good, maybe it's bad. The question is, how good or how bad is it? So the question is, if I change this, if I change my assignment on a particular dimension, so I move a little from one to the other, how does the cost change? Is it going to be a simple function? Is it going to be messy? How do I do this? So the answer is, usually, in fact in this particular example, it's actually very simple. So all I need to do is basically, I need to understand the impact on the cost of changing one dimension. So to recollect, x sub j sup I was the amount of traffic which j, the front end j, was sending to cluster I. So the question is, what impact does that one dimension change have on the overall cost of the system? And the answer is obtained by partially differentiating one with the other. And the answer has a really nice form here. What it says is, I call this the marginal cost. Marginal cost of a cluster, the front end j on the cluster I. And this marginal cost has three terms. One is the marginal latency. I send people there, they become unhappy. So how unhappy do they become? I have a per user unhappiness. What the next thing is the transit fee. I send one guy from one place to the other, it costs you PJI because it costs you per user that much. So in other words, these two are very intuitive. I send one person from A to B, he gets unhappy based on the amount of latency he experiences at B. If I send one guy from A to B, the amount it costs in terms of transit fee is PJI. Great. There is a third one which is not quite so obvious, which is my impact on the other's unhappiness. So in other words, I send a guy from A to B, there are already guys being served out there. So the more I send there, the other guys who are being served also get more unhappy, because my impact on their latency has to be considered as well. That is the third term, which I call a congestion cost. So these three together is really the impact on the total cost of the system. So there is a marginal latency, which is the user experiences, a marginal transit fee, which I have to pay, and a marginal congestion, which is experienced by everybody. So this really is how the unhappiness of the world is going to change as I change my particular dimension. Now these three, mind you, are all measurable. In fact, in the system which I am going to consider, we don't even know our C or the X, or we know the P, but we don't know anything else. You can measure this, you can measure that, and you know this value because it's a cost given to you. So the question is, now that I know what my marginal impact on the system is, how am I going to kind of change my assignment? So that's where this the dynamics comes in. So to repeat, I have currently an assignment matrix. Who is getting sent where? I want to change this matrix. I change it on each dimension separately. So I have to change really the amount that I am assigning from J to S. So J is the front end to which the request came. S is the cluster where it was served. How do I change the number of users I am sending to each one? And the answer in this case turns out to be a very nice one. And this is one called replicator dynamics. This comes from evolutionary thought. The idea is things which are doing well, you should do more of them. Things which are doing badly, do less of them. So that's pretty much all this is saying. So supposing I were sitting here and I have three options available to me. Option 1 costs say $10. Option 2 costs I don't know $20. Option 3 costs me $5. So clearly I'm going to send my guys to the $5 option. I keep doing that until the $5 becomes $10. Now the 10 and the 10, I have two of them which have exactly the same cost. Then perhaps I'll do equally until they all hit 20, and then the system is essentially stable. So really what I'm looking for is a comparison between the cost per unit for a particular option of sending users from J to S with the average cost over all the options available to me. So again, in the 3 option example, I would calculate my average cost over the 3 options, and I would know the individual cost because I calculated. If a particular option is doing better than average, which means it has lower cost, I should do more of it. So if this has lower cost than the average, do more of it. So this minus this will become positive because this has a lower cost than the average cost, so it goes up. If the particular option's cost is higher than the average, which means this is smaller than this, because this cost is lower than this thing turns out to be negative, I'll do less of it. So do more of things which work well, do less of things which work badly. And we can prove actually this is actually stable. It actually attains this point out here, that if we do this over and over again as a dynamic system, it goes to that lowest cost point which we were looking at if we use the fee in this fashion. So again, we have to consider per user latency, per user transit, and the impact on others, the per user increase in congestion. If you add up these 3 and push it into this kind of do more of whatever works for you, it actually can be proved to be optimal. And how well does it work? Now this is on something called network simulator. So basically we modified the BitTorrent client there so that you could actually move traffic from one location to the other. And so the 3 curves which we are looking at is the following. So single tracker means that we don't allow you to split. You have those multiple locations. I say I will not allow you to move your traffic from one location to the other. Now that is of course going to do very well in terms of transit fee, because I'm not moving anything, it doesn't cost me anything. But it's horrible in terms of latency, because there are some clusters which have extra load, some clusters which have less load. So the clusters which have extra load more than their capacity, they do really badly. So the overall latency goes up significantly. Now the others which I'm comparing here are the following. So this green one assumes that there is no price, no transit fee, that is. So basically it says, okay, move your traffic wherever you feel like, it's your business. Of course it does very well in terms of latency, It reduces the latency to bare minimum, but it does cost you a fair bit in terms of transit fee. The third one, which takes into account both of these and uses this replicator dynamics kind of stuff, what happens to it? It has a fairly low latency and a fairly low transit fee. We add up the two in the next diagram. Out here, what we have is the lowest possible latency plus transit fee that can be achieved with this particular load. So in other words, the assignment matrix here is the optimal assignment matrix. And the nice thing about this is it converges fairly fast. So basically, in our peer-to-peer system, which we implemented, we basically took this assignment decisions every 8 seconds. So we took a decision, measured for 8 seconds, took a new decision, measured for 8 seconds, and so on. So we measured basically the per user latency, which can be done in the cluster and fed back. We measured this increase in congestion, which is the change in latency for a change in load, fed that back. And of course, the price was known, the transit fee was known. So we took these decisions every 8 seconds, and we found in about 1, 2, 3, 4, 5. So roughly 5 or so splits, or 4 or 5 number of assignment decisions, it converges. In fact, this has very good convergence properties. So, and as I said earlier, the really nice thing about this is it is completely distributed. Each front end can take its own decision based on the costs that it sees. So you don't have to solve a centralized optimization problem. Each front end simply looks at the latencies which it sees in various things. It sees the cost and it knows the congestion because it's fed that back as well, and it takes a decision at each time based on what query shows up. Now, are there any questions on this kind of assignment problem here? Yes.
You said this was measured from a system that you built. So what did you deploy it on, and how many front ends were there?
Okay, this is actually a network simulation on a system, but it's not actually deployed. We're building a test bed, but that we don't yet have answers for. So what this is network simulator simulates the whole protocol stack, and you basically take multiple BitTorrent clients which are riding on that. So each guy comes, he starts up multiple TCP connections to various different peers, tries to get it back. And we on top of that, we built this so-called tracker system, which allows people to be assigned to various different domains. And we artificially assign costs of going to each of these domains. So under that is where our simulation is. So this is basically, we had of the order of something like, I don't know, something like 5,000 clients or so running simultaneously. And the number of times we ran it in order to get these plots, we ran the whole thing about 40 times and averaged out, and these are the standard deviation bars.
For how many front ends?
4.
Okay.
Right.
So that would affect your convergence time quite a bit, I would imagine.
That it does. But the thing is, each one has only so many options available. So the question is, how many, if you give each front end the option of choosing everything on the planet, of course it will have lower convergence time. If each front end has a set which is allowed to choose from, it will decrease your convergence time significantly. So that's the thing. So our idea was, we don't want to fetch, for example, going back to my Bombay versus Houston example, I don't want to interact with a peer-to-peer network in Bombay. I would like to interact with other things in Texas and possibly California. So the number of options should not be that high, because in any case my transit fee will get really large if I interact with multiple faraway options. So that was the object.
So I had one question. What's the addition function that you use when you sum up the latency and the transit fee?
We are just using plain addition. You can pick any convex combination, it will still work. So we basically thought latency we measure in dollars, transit fee we measure in dollars, and just add them up together. So it's just simple addition here. But you can change the constants in front, it will change nothing in the crux of the matter.
Transit fee can be latency as
well. It could be. If the transit fee itself is a kind of point-to-point link latency, it could also be in there. So it's in which case it's all latencies. So the next question we wanted to answer in this space has to do with admission control. The idea is, supposing my clusters are of a certain fixed capacity, whatever it is. So, and supposing the load is much higher than that, then there is no assignment on the planet which will reduce my latency to an acceptable level. So at that point, I need to know what to drop. How much can I admit? How much do I drop? So the kind of idea expressed here is that given a particular load vector, I know how to minimize the total unhappiness of the world. But then this total unhappiness of the world which is minimized might itself be unacceptable, because there's simply too much load. in which case I better start dropping some of them. And how do I drop? So the idea is that each user has a happiness associated with himself that can be thought of, supposing for example each user brings $1 worth of happiness. So each user pays me $1 to be serviced, in which case the rate at which users arrive is xj, the rate at which each guy brings $1, in which case this log won't exist. I will just have dollars times x. So each user brings $1 and I try to minimize the happiness minus unhappiness. In a kind of generalized setting in network optimization, we often consider concave increasing functions like log. The idea is that the marginal impact of each user becomes lower and lower. Like for example, supposing I have a query which consists of say a request for search results with images, with ads and so on. So each marginal part of this. So I guess the search results are really important. It's this big text, bunch of text which I need. The images are perhaps slightly less important. Then perhaps the ads, I don't know how important they are. I presume they are important. But the question is how. So at some point you have to decide which is more important than the other. So this idea here is that the log tries to indicate that the marginal impact of the increasing number of queries, somehow it is important. It does increase your happiness, but it doesn't increase it as much as in a linear fashion. So if I have 3 queries, my first query must be handled. The second query perhaps not so good. The third query perhaps even less so. That kind of thing. So this will work of course for linear, log and a whole bunch of concave functions. So but in general the high level idea here is you want to maximize the sum total happiness minus the sum total unhappiness. So just to put this in the right framework, the load assignment problem's job is to just minimize total unhappiness, whereas the utility maximization problem is to maximize the total happiness, which is things which make me feel good and things which make me feel bad. So the question is, how am I going to do this admission control in a simple distributed fashion? So essentially what this means is each of these front end servers has to decide whether or not to admit a query, and it needs to do so understanding what the impact of that query is going to be on the happiness of the system. So really, if this is the total happiness of the system, I need to know what the impact of changing that x, which is the load which is coming in on the system. In this case, it turns out it's a very simple function. We just have to differentiate with respect to xj. And what we can do is use something called a gradient ascent type controller, which essentially says if something is increasing the cost, then cut down on it. If something is decreasing the cost, go up. And we implemented this as well on our NS2 thing. Whoops, I went backwards. Right. And so these 3 colors now are completely different. Basically, there's just one system with 3 front ends. So there's a blue front end, a red front end, and a green front end, and they have to take admission decisions. And the objective here is to show that although they take their admission decisions in a distributed fashion, it does converge, and the total system happiness also converges. So the idea is that somehow in a distributed fashion, I need to minimize cost and maximize happiness. So that is what is being done here. This interestingly is about 7% from the optimal solution. This is again being done over a huge number of BitTorrent clients, with actually in this case it was 3 front ends. So now, so the key insight from this part of the talk is basically that it is possible to align incentives in terms of end user latency and cost objectives, and it is possible to do it in a distributed fashion in a fairly simple way, because everything that you need is measurable. So I don't even need to know the capital C, the capacity. I don't need to know the load. All I need to know is this marginal impacts, which can be measured, because I can measure latency, I know cost, I can measure congestion. So ongoing work in the P2P space, capacity changes in a weird fashion, because people come, people leave, and the question is how do I incentivize people to stay and serve other guys? And also we're just working on, this is a very simple testbed which we want. We just want 3 servers right now, in which are connected by real network links with a certain cost, and want to see if this performs as it should. So that's the current state of that. Any further questions on this part of the talk? Yes?
Have you considered what happens when the prices change over time?
When the prices change over time. Okay. So if the price is going to change over time,
So it's like cheaper during
it's
the night and so forth.
so then okay. If the question, over that time scale, nothing will change, because the convergence of the innermost loop is of the order of actually 40 seconds to a minute. So if your prices change of the order of days, no change whatsoever. It'll converge long before, and it will keep converging. So any further things?
So what happens when you actually drop it? I mean, in a real system, wouldn't the client then just try again, and then you're
Right.
still paying that transit cost and everything? I mean,
If you drop it, you'll drop it again. So basically, once you've got this value out here, this is really the supportable traffic. So basically, this says, once it's converged, that if I want to maximize the happiness of the world, this is the amount of load I can support. So any further load, I just have to keep dropping.
aren't you though paying that transit fee every time the request is made, because you're not making that decision to accept it until it arrives at the server?
Right. So you okay. The query itself, as far as P2P goes, the query itself is just this tiny thing saying give me a piece or give me part of the file. The transit fee actually is in the service itself. So once I've been accepted, shipping the traffic across
so
the
it's actually
cost.
not when you say the cost is a per query basis, that PIJ, it's really only the response. It's
Yes,
not the
the
actual
service itself. Yes, if I decide to accept it. Otherwise, I just drop it. Yeah. Although in the admission control problem, the admission control is done at the front end where it originated. So you won't even, the query won't go across to the other side if I'm not going to accept it in the first place. So what I'm trying to get at here is, I've got, this is a good picture. So here is where I take my admission decision. So I won't actually send the query there if I think that it's going to have a bad impact on the system. So once you're dropped here, you're dropped. So you might come back, you might be dropped again. So it's only if I think that the system performance is not going to be massively impacted by you that I accept you, and in the inner loop I decide where you're going to be shipped. So the inner loop decides where to move users around. The outer loop decides whether or not to admit them in the first place, if they have been.
Yeah, no, I was just thinking about it from the search problem where the actual transit cost is the additional latency, and there you're, that's being paid on the drop. It takes you that much extra longer to decide that your query is not going to be serviced.
Actually, no, because it's dropped at source. So if anything, it will add to the latency of the query processing engine, as in the front end, this front end, not that one.
Okay.
So in other words, you're dropped where your request originated. So there's.
So when you talk about congestion, do you also consider the decrease in congestion? Let's say I go from 1 to 2, so you talk about the backend 2 increase in congestion. Do you also take the decrease in congestion at 1? Do you sum it up over all the?
That's where this stuff about comparing with the average happens, because I compare. So the query comes here, and I compare the latency out here with the average over all the options available to me. So I'm inherently comparing what would happen if I sent it locally. Because it's doing better there is why I send it there. If it were to do better locally, I wouldn't even bother. So yes, there is a comparison there. It's implicit. There's no explicit comparison between the two. All right, I'm actually running out of time, but nevertheless, let me talk about this stuff about flash crowds. Yes, that's out here. Oops. Right. So the idea here has to do with how do I share files when they're very, very popular. So the question here is the following. This is a cute little graphic from Pando again. So Pando basically says, if I have a CDN only, you can think of it as big server. As I have more and more people who request the content from the server, there's worse and worse performance because the latency is bound to increase in exactly the same convex fashion. And if I want to service them at a given quality, I either have to provision a lot, which is higher cost, or those guys will be unhappy with me and leave, which again means a decreased revenue. So the point is that if you can somehow utilize end user resources, and you can think of these end users. One possibility is to think of them as caches, which are closer to the end homes, perhaps at the POP level, or perhaps even at the cable head ends, or you can think of them as end users like you and me. So basically, the point is, if I can somehow utilize the resources lower down in the hierarchy, then more and more users or more viewers of this content might mean better and better performance, simply because there are so many more copies of it available, and you can lower your cost because you don't have to unicast all the way from your server. So the question is, how are we going to combine these two methods? the server-based and the peer-to-peer based. So before we ask how do we combine it, we need to know what kind of load we are likely to see. So this is an analytical model for describing such things. What it describes really is a viral distribution, viral propagation of interest. So I of t is the number of people who are interested in a particular piece of content at some time. So this is the total population of guys who say I want it. Now how does that change with time? So this is called the Bass diffusion. This comes from Frank Bass's work in 1960s, where he was looking at the propagation of interest in microwave ovens. So there's this new gadget, this microwave oven. How do people request it? What is the rate of change of interest in such things? Now this has been used much earlier in population dynamics, in viral models and so on. The idea is the following. So there are so many interested people right now, right? And n is the total number of people. So n minus I are the people who aren't interested right now. If I advertise, it reaches a constant fraction of the people who aren't interested. So k is a constant which describes my advertising budget. Maybe I do television, billboards, whatever, and it reaches some constant fraction of the population. On the other hand, people tell each other things. So each guy who's not interested might tell the guy, hey, this microwave oven is so cool. So people who are interested pick somebody at random and say this is interesting. The probability you find somebody who is not interested is the number not interested by n. So really this captures two effects, an advertising effect and a viral effect. Now very often in things like YouTube videos, for example, there isn't very much of an advertising effect. It's by and large viral. So for a file distribution of this kind, we're going to drop the advertising and look essentially only at the viral propagation. Although the results which I'm going to talk about essentially hold for that as well, the advertising as well. So we can solve the differential equation explicitly. You see this all over the place. This is the number of interested people, and it follows this so-called logistic function. The idea is initially nobody much is interested. People start telling each other. At some point, suddenly you have this growth. This is an exponential growth at that point, and then it levels off. This is characteristic of what is called a flash crowd. Essentially, the idea is at some point you see sudden increases in interest of something. Question is, how am I going to service this interest? Okay, this is fairly common. I work with a guy called Mike Friedman who runs a content distribution network on called Coral CDN. It's based on Planet Lab, which is this university network, and he hosted a whole bunch of files on it. In particular, tsunami videos. Basically, when the Asian tsunami struck, there were lots of home videos, and this is one example of such interest growth. You have this sudden spike of interest. All right. So what am I going to do? I can use the CDN, which I call a bank of servers. I can use peer-to-peer, or I can use both. And since I'm giving this talk, I'm going to basically show that hybrid has some phenomenal performance improvements. So a little bit of notation again. I of t is the number of interested people in this file. It's the cumulative demand. P of t is the number of people who possess the file. It's the cumulative service. So I really need to just work with these two. And I'll say why this total latency is the area between those in just a second. So I have a server. It has a capacity C. How am I going to kind of understand the latency experienced? So what happens is this blue curve is the demand, the I of t, and the green one is the service curve. So what happens? Initially, very few people ask me. So the rate of request is much lower than the capacity. I can serve it pretty much instantaneously. So it goes along there. At some point, the rate of requesting is more than the capacity available. At that point, I see this divergence. So the idea here is, so if somebody shows up here, so the blue curve is demand. So somebody showed up at this time. He got served at this time. So there was a little delay. So as time progresses, since the arrival rate is so large, somebody who shows up here got served here, shows up here, got served here. So this area between the curves is the latency or the delay experienced between the demand and service. So the slope of this curve is the capacity, because the server is running at capacity at this point. It simply cannot keep up. At some point when the demand slackens off again, it catches up. So great. So basically we have this knee when my server just gives up, and eventually it will catch up, and the area between these curves is what I'm interested in. Now I can actually analytically characterize these exactly, and the area scaling looks like theta n squared over c. Don't bother to remember this for now. I'll do a comparison at the end. But it's just intuitive to realize that this looks kind of like a triangle, because the interest looks almost like a staircase and the service looks almost like a straight line. So the area of the triangle roughly gives you the intuition, although we can do an exact calculation. N is the total number of interested users. Yeah, finally. The service model for peer-to-peer is essentially the same kind of thing. It's basically if I'm interested but I don't have it, I ask somebody at random, and if they have it, I can get it off them. So really the thing about this is the interest and the possession couple into each other, because only if I'm interested will I ask, only if I have can I serve. So that is the point. This too can be solved explicitly. It gives you a green curve which looks like that. The interesting thing here is initially nothing much happens. All the way I ask people, do you have it? Well, they don't have it. So nobody has it, nothing happens. But once a small number of people have it, it just shoots up exponentially, because each one can serve a whole fair number of other guys. So basically, until about log n time, nothing happens, and by 2 log n time, everything is over. So again, we can characterize this area. And the most interesting thing is the CDN does well initially until the server is overloaded. P2P does well once the installed user base is large, once some number of people have it. So how do I combine them? I first use the server, then I use P2P, and we can show that it gives you very good improvements. So I'll give you an example here. Supposing I used the server capacity n by log n. N, recollect, is the total number of users who are eventually interested. The server alone, or the CDN, can give you latency of the order log n. P2P alone can give you log n. The hybrid, though, can give you log n, which for fairly large values is essentially constant. Further, I use this server only for a very short time, only for log n time in the hybrid case. So the thesis here is that you must serve for a short time using your server, at which point your P2P has enough capacity to really ramp up. So these are simulations in the space. So the first one is the server based, again demand supply. This is the peer-to-peer one. You can see there's significant areas between these curves. Essentially the per user average delay was of the order of 10 seconds here. Here it's of the order of 1 second roughly, because the area is much lower. I do server first, then peer-to-peer. And well, then the question arises, what happens if I do both simultaneously? Answer is not very much, because if I first ask the peer and then ask the server, initially everybody gets served by the server. And so this pink line is the amount of server usage. So initially everybody is getting from the server, but once you hit a certain value, nobody much, it just levels off, and most people are getting it using the peers. So again, this just reinforces the idea that an initial boost using a server is what a peer-to-peer system needs. You do that boost, and the peer-to-peer can take over after that. And this is true of CDNs like Akamai as well, where you might want to do unicasts to the caches at an initial amount of time, after which the caches themselves can handle it. So I think I should stop here and take questions. If you're interested in peer-to-peer streaming, I'm around, as I said, at Stanford till the end of next week. So please do send me an email, and we can discuss some of this. Also, I've given Andre the papers in this space. And so I will just stop here and say thank you and take questions. Thank you. Anything further?
One thing is, when I'm talking to a peer,
Yes.
I always run the risk that that user randomly decided, so okay, I'm not interested anymore, now I'm walking away.
Right.
And now I get, even if it's just for a short time, I get a timeout, so my service is worse than if I would be connected directly to
Right. So the way we are implementing this, or the way we are looking at how it should be kind of implemented, is as a feedback system where I keep track of my, my average rate, and the system as a whole has a target average rate. If your rate falls below a threshold, the server should boost you. If your rate is above the threshold, you're fine. So you might get timeouts, but this is on a per chunk basis. So in other words, there might be a few chunks which you might have a lower rate for, but the server will quickly boost you if your service rate falls below a threshold. So essentially that was what I was talking about here. In the case where people aren't leaving, I've done simulations on when people leave. Even there you get significant improvement. Here what I was saying was if people don't leave, the server is not used after a while. It just remains constant. So this is the cumulative. So essentially if I looked at the derivative, this would go to 0 after a point. But so the server is essentially used only initially for this. Now if people start leaving, again the number of people who possess, which is this red line, would kind of go down, in which case the server will be used again in the end. We did some simulations on that for various different departure rates. Even there you do get significant improvements in the amount of server usage. So the server can be multiplexed over multiple pieces of content, rather than having to serve everybody through the same unicast. So yes, as long as there are peers in the system, you use them. If at any point it falls below that your service is bad, your feedback loop will take care of it by boosting using the server. So that's how you'd want to combine the two to ensure quality of service guarantees. Anything further?
Yes, so have you looked at the social aspect of P2P? Is like the P4P work that you mentioned.
Right.
So they have this like you connect to your social network, and the whole fact is that you incentivize your social network. So like BitTorrent by default, you
Right.
know, has the initial upload rate which is same for all the peers it is connected to. Whereas I had done some work in this, and P4P work was more extension of that, and they've seen like up to 20 to 30% decrease in the total download time when you use this aspect. So have you looked at this?
What we are looking at actually is kind of like an exchange kind of situation. Like essentially, I have content, I have bandwidth, I can sell it to somebody essentially. So we're looking at it as a distributed market system. Now, we looked at the prices there as the best thing I can get. Now, if you're my friend, I might want to subsidize you. That is an aspect which I've not considered. But I've been looking at peer-to-peer as an exchange economy, where you essentially can exchange your resources for somebody else's resource. So yes, some work, but not in the context of friends giving to other friends for cheap. So no.
There has been some work about making sure that seeds stay in the system. Have you heard of BitTyrant?
Yes. So yeah, there's a lot on how to incentivize users to stay. One way which BitTorrent automatically does is it just kind of slows you down at the end so that you have a little more. So
Yes.
I think these incentives have to be considered. So if you look at it, as I said, as an exchange economy, many of these incentives are automatic because I'm staying because I make some currency, and I can use that later on for something else which I want to download. So answer is there is a lot of space in this regime, but one question which automatically arises though is who owns the content. So if I am making money out of the content through kind of uploading it to somebody else, am I somehow kind of withdrawing or detracting from the amount which would be made by the owner of the content? So I don't know, some kind of scheme like the way the Google does it. Each publisher will get a small amount of money based on visits to their web page and clicking on ads, might be a feasible solution. So it's unclear how to create such exchanges. I mean, as in how the currency mechanism would actually work. But we can show you get significant improvements if there were such a currency. So yes.